Okay, we're continuing in 15.3 and we're looking at the subject of counters. In essence, a flip-flop that is configured to toggle on every clock pulse is a 1-bit counter. If multiple flip-flops are connected together, a counter of any length can be built. There are two general classes of counters. They are the asynchronous variety. Clock pulses arrive at the flip-flop at different times, and then there are synchronous, when the clock pulses arrive at the flip-flops at the same time, meaning that the clock pulse is simultaneously fed into all of the flip-flops at the same instant. Here we have a JK flip-flop, and one of the essential points of doing counters is the ability to divide by 2. And so a flip-flop will effectively divide the incoming frequency by 2. And so let's look at how that occurs. First of all, with a JK flip-flop, if we have the J and the K inputs both set to 1, then it will, if you recall, this will cause it to toggle, change the output changing with every clock input. And so here we have a external clock, and we would be feeding in a pulse to the then this would be the clock input, and you'll notice the little greater than symbol that indicates that it's going to be clocking on positive going clock pulses. And so here we have a clock pulse coming in, and we'll just start it right here. Here we have the incoming positive edge, and what we'll note here is on the incoming positive edge the output goes to a 1, so that would be a 1 and a 0, and obviously the Q naught would be 0. Then as the cycle progresses, it goes negative. Nothing happens as it goes negative, and then as it goes positive, again the output of the flip-flop changes state, so now it goes to 0 and 1. And then we go on, and the next positive edge, again, it changes states here, and so then we go to 1, 0, and on every positive edge it's going to change states, and so we have a resultant output of and this is the resultant output right here. But of note is that you see this frequency coming in and you see this frequency coming out, and what can be observed is that this frequency is twice this frequency. So a flip-flop coming in that is configured like this will toggle, and the output will be half of the input frequency. Now here we have a flip-flop, or excuse me, a counter, and this counter is going to be a 3-bit counter, and you'll notice we have flip-flop A, B, and C. And this is actually figure 1526 in your textbook. And these are, we have a circuit that we're going to talk about later. Well, in fact, it is this circuit, but we will actually see the simulation later in this presentation. This is the actual outputs of this device. Now, first of all, I want to bring your attention to this concept again of dividing by 2. And we're going to be looking at these outputs here, having defined what they are. This is output of A, this is B, and that coincides with the outputs A, B, and C of this flip-flop. And you'll note here we have the incoming clock frequency, and the output of C here will be, which is what we just previously looked at, would be right here. And you'll notice that it is half the frequency of the clock frequency. And then if you compare C to B, what you'll observe is that B is actually half of C. And likewise, if we go up to B and then compare it to A, we'll note that A is half of B. And so if we were to look at this and assign weights to it, A would be, we'd have 1 cycle, and then B we would have 2 cycles, and then C there would be 4, and then the clock would be 8. And recall that when we did our binary weighting, and we set up, and we said 1, 2, 4, 8, 16, 32, and so on and so forth. This was the way that we weighted binary values, and so if we said that we had a and since this is 3 bits, if we had a 1, 0, 1, we said that that would be 4 plus 1, and we said that equaled 5. But this frequency division sets up a scenario where we're going to be able to actually count. And let's take a closer look at this particular waveform. And if we will note here, we notice that at this point we have a 0. This is a low, and a low. And that would equate to 0. And notice we have a counter here. This is counting from 0 up to 7. And that would be right here. And then the next one, we have a 0, a 0, and a 1. And that would be the 1 which is right here. And then we go on. Here we have a 0, 1, and a 0. That would equate to 2. And let's see, then we have a 0, 1, 1. That would be 3. And a 1, 0, 0. That would be a 4. 1, 0, 1. That would be a 5. And a 1, 1, 0. That would be 6. And then finally 1, 1, 1. That would be 7. And then it resets and goes 0, 0, 0, and then it repeats this process. But that is essentially what we do with a counter, and it utilizes this divide function, and we see the results here, where we are actually, and you can see the pulses that will indicate these different numbers. Now, we do want to look at how is it that this actually works, because there is a specific methodology that makes that process happen. So on this particular screen, I've taken the same schematic. I've made it a little bit larger, and then we also I've taken the timing sequence and enlarged it a little bit as well. So let's review a little bit here. Let's see. We had, again, this is A, B, and C. And this corresponds to flip-flop, the output of flip-flop A, B, and C. And our counting, let's see, we would have, this would be starting at 0, and we would count up through 7. Now, let's look at the initial state of this circuit. Notice that we have the clock pulse coming in right here. And notice that the clock pulse, this is a synchronous counter, and so what that means is that that clock pulse is simultaneously fed into all the flip-flops at the same time. And so it will be clocking them depending on what is at the input of the flip-flop. Now recall that in this particular case, there will either be zeros on the inputs of the J and the K, or there will be ones. That is the only two options we'll have in this circuit. And so remember that if there are ones on the inputs, then it will toggle. If it is zeros, they will just stay in whatever condition they were in, and they will not change. Now, of note, we have a positive voltage here, and so that will put a high here and a high here. And so what will happen is that flip-flop C, which output QC right here, will toggle on every input, every clock pulse that comes in. And so this has little bubbles here, and so you'll notice here we have the negative edges occurring here, 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 and all the way across. And on every negative edge, this one is going to count. And this is effectively our one. Remember, we have the 1, 2, and 4 in our weighted positions in binary. And this is effectively our ones digit. And so it would be expected that it is going to toggle on every single count, but that our 2 and our 4 will not. Okay, so in the initial state, when we are at 0, 0, 0, we're going to, let's look at the state of our various flip-flops. This has a 1 and a 1 on it, so it will toggle from 0, 0, 0, it will toggle to 1 on the first clock, because it has the appropriate inputs on J and K. Now let's look at the inputs on flip-flop B and flip-flop A. Now, notice the output of C comes over here and it feeds into JB and KB, which is flip-flop B. Now, recall, initially we are at 0, 0, 0. So initially this is feeding a 0 here. So on the first clock pulse, this will not change because there is nothing there. There's no voltage, or there's a 0 here, so it will not change states. Now, so B won't change. Now let's consider A. Now, when we have at 0, 0, 0, let's look at the Q naught positions. Q naughts, they should all be high. 1, 1, and 1. Now, what feeds into the, in flip-flop A here, the J and K inputs are fed by this NOR gate. Now, notice we have the QB naught comes up here. It has a 1 on it. And QC naught also comes up, and there's a 1 here. So a 1 and a 1 going into this node, that's going to result in a 0, so there will be a low on both of these inputs. And there will be a low on both of these. Now, this represents the initial state. So when that first clock pulse comes in right here, excuse me, it's not going to, this is for 0, it'll be actually right here. And it will cause this flip-flop to trigger, and it'll place a 1 on the output, and probably just indicated here. It places a 1 at QC's output, and we have the count of 1, and these two will remain at 0. Now, at 1, notice that this output goes over to J and K of B. And that is going to change these two. We're going to have a 1 here now. And so here we have 1, and then this was our first clock pulse right here. Then here we come, and here is our second edge. Now, our second edge is going to do something interesting. Remember, this one toggles on every one, so this output is going to change to 0. But recall that when we had 1, there was the 1 sitting here. So there's a 1 on J and B at the time of this edge. So the output of B toggles to 1. Okay. So here we have the toggling action here, and so here we have a 1 and a 0. And so that reflects the output of B and C. So now we have the count of 2. Okay, now at this point we're at 1, 1, and 0. We're at 2. Notice this 0 is fed over here, and now there is a low here. Now that is significant because when we count to 3, which is going to be right here, when we go to 0, 1, 1, this has to remain the same. We were at 1, 0. Now we want to go to 1, 1. Well, this will stay a 1 because this 0 here is fed here. When the clock pulse comes in, it won't change states because if there are zeros here, it just remains as it was. So that will give us 1, 1, or 0, 1, 1, which gives us 3. So at this point, we are at 1 and 1. We have counted to 3. Profound, huh? Okay. Now, when so 0, 1, 1 is our current output. Now, on the next clock pulse, this one is always going to change. And recall that we have a 1 going over here, so there's a 1 here. So on the next clock pulse, it will toggle from 1 to 0. Okay, and so that will give the count that we're going to is going to be 1, 0, 0, which is 4. But we're at 3 now, so we can see that these two will change. This one has to go to 1. Now let's look at the conditions that will make this go to 1. First of all, this is a 1, this is a 1, so that means that we have a 0 here and a 0 here. So the QB naught and the QC naught are both zeros. If they come up here, notice what's going to happen. We have a 0 and a 0. That will enable this NOR, so then we will have a high right here. So that will put a high on QA naught. Now what that will do, on the next clock pulse, we know that this will toggle to 0 and 0, this will toggle to 1. And so that will give us 4, which is right here, which is 1, 0, 0. Okay, so now we're at 1, 0, 0, and since we're at 1, 0, 0, we need to note something about this gate. When we toggled to 1, 0, 0, that changed this to a high and this to a high. Both QB0 and QC0 went high, so that changes both of those to 1, which makes this 0. And so what will happen is on the next few counts, this is simply going to remain as a 1, because the only time that this digit will change is when both of these are high. And so through the next couple counts, these are going to go to 1, and then 2, and then 3, and then it will switch again. But at least, because for count 4, notice for count 5, 6, and 7, this has to remain high. Okay, so we are at count number 4, and there's a 0 going over here. So to go to 5, we need to go to 1, 0, 1. Now, in order to do that, this has to remain the same, and since this is a 0 from QC, this will not toggle, but this will always toggle because of the fact that we have the 1s here. And so that would give us 5, and so that would be 1, 0, 1. Okay, the next one, let's see, we're at 1, 0, 1. Then the 1 from QC goes over to our J and our K inputs here. On the next pulse, QB will toggle because of that. QC will also toggle, but they're just going to flip-flop, so we are at 1, 0, 1. So then we'll be at 1, 1, 0. And again, okay, we're at 1. Now we're at, let's see, I had to find a place to write these. I guess we'll just write them down here. We're at 1, we were at 1, 1, 0. That gives us our count of 6. And since we're at 0 here, on the next count, this will not toggle because there's zeros on the B. C will always toggle, so then we'll have 1, 1, 1. Okay, now the next one is a critical count because we have to go from 1 and effectively reset to 0. Now, the way this is going to occur, notice this one will always toggle, so it will go to 0. Notice we have the 1 going over here to this, so this one is going to toggle. And since we have the 1 here and the 1 here on the B and the C outputs, the QB naught and the QC naught, again, they're at that 0 state. That is the only state that causes this to be enabled, so we have a 1 here. So we have 1s on all of the JK inputs, and each of the states of the JKs are 1s, and so on the next clock pulse we will go to 0. And so that is the basic theory of how a counter works, and this is a synchronous counter. Now, this particular image right here, this is a simulation of that particular circuit. Now, you'll notice there's a lot more wires in it because we've got to, the clears and the sets have to be in there, and then we have added these little light bulbs for illumination. Now, what you can do, and I encourage you to do this, this is going to be circuit 1526, is to do this simulation, and when you turn this on, you're going to see these lights illuminate, and these lights will represent the counters. In fact, when you start, it'll be 0, 0, 1, and this, and what you see here is count 5, because this we have 1, 0, 1, and you'll be able to see it count. Now, to see it may be going very fast. What you might want to do is go in and click on this clock and set the frequency of the clock input down, so then you can see them. I think it's set to 1,000. If you set it to 100, then you can see it count very methodically. Then this device over here, I'm going to just point to it. This is a logic analyzer, and if in electronics workbench, if you click on that, that will give you. Let's see if we can go back to. This is a part of that. This is this graph right here. It will show you the various outputs, and in fact, in your simulation, this third input is not in it. You'll need to draw a connection here going down to here, so you can see the actually the output of the C flip-flop. Okay, that pretty much wraps up the theory of this. If I can get the simulation to run on, I may add a little piece to this to show this in action. If that doesn't occur, in fact, I want you to do this anyway. I want you to go and look at this and simulate it yourself. So that concludes our discussion on counter